Okay, well, that's very interesting. Here, let's look at a simple system, a system that is an example of a central potential problem, but it's so simple that we can figure out the energy levels without doing a lot of math. The system we're going to look at is called the rigid rotor, one of my favorites. All right, here, let's take a look on the notepad. All right, so the rigid rotor is something like this. Okay, imagine two masses connected by a rigid rod. And the only type of motion that we're interested in is rotational motion about the center of mass. Okay? Imagine such a system, but so small that quantization of angular momentum plays an important role. Actually, we don't have to imagine this. Systems like this are very common. Diatomic molecules are excellent examples of rigid rotors. In any event, for a rigid rotor, we can figure out the energies just by looking at quantization of angular momentum. Why? Because for a rigid rotor, if we ignore translational motion, the only type of motion the system can have is rotation about the center of mass. And in that case, the only kind of energy the system can have is rotational kinetic energy. I mean, it could have mass energy and other things, but those other energies never change, so they're unimportant for our discussion right now. So the energy of the system is its rotational kinetic energy, and we know that the rotational kinetic energy of a system can be written this way: L squared over 2I, where L is the magnitude of the angular momentum, and I is the moment of inertia of the molecule or system. Okay? Which we can easily figure out if we know the geometry of the molecule. Okay. But what's interesting is that quantization of angular momentum tells me that the energy has to be quantized too, because L squared is just going to be given by the square of this quantity here. So that's L times L plus 1 times h bar squared over 2I. Okay? And we'll write this as an expression for the energy, which we'll write as E sub L, since clearly the energy is quantized and depends on the quantum number L. And just as before, L can take on only integer values. Okay? Wow, we're done. We figured out the energies for this system without actually having to do any work. Here, we can make a sketch of the energy levels of the system. The lowest energy state is the state that has L equals 0. And of course, that has energy 0. The next state is the state with L equals 1, okay? And that has an energy of 1 times 2 times this quantity here. I'll just draw it here, and we'll notice that it's 2 units of energy. What about the next state? What's that? Actually, see if you can figure out the next 3 states, okay? Take a moment to do this, and then you'll answer a question. All right, did you figure it out? So the next state is 2 times 3 times that quantity, so it's 6. The next state is 3 times 4 times the quantity, so it's 12 units. 1, 2, 3, 4, 5, there we are. The next one is 20 units. So in every case, it's 2 or 6 or 12 or 20 times this quantity. h bar squared over 2I. Pretty cool. So those are the energy levels for a rigid rotor, okay? Now, did I mention that there are lots of physical examples of rigid rotors that, in particular, diatomic molecules are excellent examples? So we can actually look at some data for a diatomic molecule. And to do that, we should just do one more thing. We should look at the transitions between states. So there's actually a selection rule for transitions that result from absorption of or emission of light. And that's that the change in L has to be equal to plus or minus 1, okay? And this comes about because of conservation of angular momentum. It turns out that photons carry 1 unit of angular momentum. And so they can either increase or decrease the angular momentum of the molecule by 1 unit. But that's the only choice if we're only going to absorb or emit 1 photon. Okay? Okay, now if we're absorbing light, then we have to increase L because the energy of the molecule has to increase. And in that case, HF would be equal to the final energy minus the initial energy, which would be, let's write it this way. Okay, excuse me one moment. Very good. Let's imagine a transition from the state L minus 1 to the state L. And now let's find the difference in energy between these. So simply multiplying these out, we get L squared plus L times h bar squared over 2I minus L squared minus L times the same quantity. And you can see that the L squared terms cancel out and the other terms add so that we get 2 times L times h bar squared over 2I. Okay? Very good. Or here, this is a little silly. Let me just simplify this. We have L times h bar squared over I. And that's the transition energy between successive states. Notice something interesting. As we increase the quantum number associated with the transition, the energy of the transition also increases in proportion. Okay, so it gets larger and larger. Here, let's take a look at some data. Okay, 1 second. There we are. Excuse me, let me get my laser pointer here. There we are. So in this case, our rigid rotor is just a carbon monoxide molecule. So it has an oxygen atom bonded to a carbon atom, okay? And this is an excellent approximation of a rigid rotor. The energy states for this system look like this, okay? And and what we're going to observe are transitions between energy states, 0 to 1, 1 to 2, 2 to 3, and 4, and so on. And you'll notice that as the initial state quantum number increases from 0 to 1 to 2 and so on, that the transition energy also increases, and it increases in proportion to L, okay? So what this should produce is a set of equally spaced lines, one at h bar squared over I, one at twice h bar squared over I, one at 3 times h bar squared over I, and so on, okay? Now let's look at the data. So this is an infrared absorption spectrum in the long wavelength part of the infrared. Okay, here's the light frequency in units of 10 to the 12 hertz or terahertz. This number, wave numbers, that's 1 over the wavelength. Okay, and then what you see is a series of absorption lines. And notice that they're equally spaced. And they are the 2 to 3 transition, 3 to 4, 4 to 5, and so on. The transitions that occur at lower frequency are outside of the range of this measurement. So the data is too noisy. Okay, but we see these equally spaced lines in absorption. And this is a direct support for the rigid rotor model of this molecule. Okay, and so it's direct support for quantization of angular momentum. The reason we see equally spaced absorption lines is because angular momentum is quantized. Finally, we can get some useful information from this. Since the spacing between the lines is just h bar over I, where I is the moment of inertia, we can use this to determine the moment of inertia of the molecule. And since we know the masses of the atoms, we can use that to determine the length of the bond between the atoms, or the size of the molecule. Okay, so useful as well as interesting. Anyway, I wanted to show you that example, and now I think we can stop. All right. Okay.